Quarter wave transformer. Actually, we have studied quarter wave transformer in chapter 2 in a very brief way. Here we are going to study this quarter wave transformer in more details. Quarter wave transformer is used to match a real Z load to a transmission line of characteristic impedance Z naught, where Z load does not equal Z naught. In chapter 2, we proved that if we have added a transmission line section of length of lambda over 4 with a characteristic impedance which has the geometric mean of Z load and Z naught, such that Z1 equals square root of Z naught multiplied by Z load. This is the geometric average or the geometric mean. Then the input impedance at this lambda by 4 transformer would be Z naught in this case. Actually, we calculate this transmission line or this lambda by 4 transformer by using the input impedance of terminated transmission line. As a tuning circuit, quarter wave transformer is very simple and useful circuit for matching real load. But actually, it can be used only for real load. So, for matching real load impedance to a transmission line. We already studied using one section of length lambda by 4 with a characteristic impedance which has the geometric average between the load and the characteristic impedance of the transmission line. But this theory can be extended to multi-section lambda by 4 transmission line sections. That's what we are seeing. Quarter wave transformer can be extended to multi-section designs to provide broader bandwidth. If only a narrow band impedance match is required, we can use just single section transformer and it would be quite sufficient in this case. Actually, the main drawback of quarter wave transformer is that it is only suitable for real load impedance. So, if the load impedance is not real, we must make it real. This can be done by adding a shunt susceptance or a series reactance, or adding another transmission line section such that the input impedance after this transmission line section is converted to pure real value. Maybe it will not be Z naught, but this would be a completely real value. That's what we are seeing here. A complex load impedance can be transformed into real impedance by using an appropriate length of transmission line between the load and the quarter wave transformer, or by using an appropriate series or shunt reactive element. Actually, the disadvantage of this solution is that if I have added a shunt stub or a series stub, actually this stub is appropriate for center frequency. The question is, what will happen along a certain bandwidth? Along a certain bandwidth, this shunt stub or series stub will not have the exact susceptance or reactance which has been designed at the center frequency. So in this case, the load is not real once again at slightly different frequency from the center frequency. So these techniques will usually alter the frequency dependence of the load, and this often has effect in reducing the bandwidth of the matching circuit. So maybe the matching circuit itself as a quarter wave transformer or multi-section quarter wave transformer has a wide bandwidth, but the shunt reactive part or series reactive part or the transmission line section which is added to convert the load to be real impedance, all these solutions are narrow bandwidths. So the total bandwidth of the circuit, including the quarter wave transformer and the reactive part uh, isolation or reactive part subtracting part, uh, all these parts should have small bandwidths, not because of the transformer, but because of the shunt or series stops, or because the transmission line section added to the load. The analysis of quarter wave transformer. If we have a real Z load connected to a transmission line section of characteristic impedance Z naught through a transmission line section transformer of characteristic impedance Z1 and length L, the input impedance seen at the end of the transformer is given by Z input equals the characteristic impedance of the transformer Z1 multiplied by Z load plus J Z1 tan beta L over Z1 plus J ZL tan beta L. We are going to replace tan beta L by the symbol T. Okay, and actually beta L correspond to the phase shift due to the wave propagation along the length L on the transformer section. So we can replace the value beta L by theta. For the quarter wave transformer, at the center frequency, the value of beta L or theta equals pi over 2. Actually, at the center frequency, the length L is lambda by 4 and beta is 2 pi over lambda. So 2 pi over lambda multiplied by lambda over 4 equals pi over 2. So at the design frequency or at the center frequency, the value of beta L or the value of theta equals pi over 2. This theta corresponds to tan beta L tan pi over 2 equals infinity. Alright? So at the center frequency, the input impedance equals Z1 multiplied by ZL plus JZ1 multiplied by infinity over Z1 plus JZL multiplied by infinity. Let us assume that it is not pure infinity, it is very large value. So at theta around pi over 2, the numerator here nearly equal JZ1 multiplied by T, while the denominator nearly equal JZL multiplied by T. By taking the limit, T can be eliminated by T. So in this case, the input impedance, it would be Z1 multiplied by Z1 over ZL. Or in other words, Z input would equal Z1 squared over ZL. And it is required that the input impedance at the second terminal of the transformer would be Z0. So Zn at the center frequency, which equals Z1 squared over ZL, would be Z0. Or in other words, Z1 squared equals Z0 multiplied by ZL, which means that the required characteristic impedance of the quarter wave transformer Z1 equals square root of Z0 multiplied by ZL. This is the input impedance at the center frequency. The question now is, what would be the reflection coefficient as a function of frequency, not exactly at the center frequency, around the center frequency? We can obtain the reflection coefficient gamma as Z input minus Z naught over Z input plus Z naught, where Z input is Z1 multiplied by ZL plus JZ1T over Z1 plus JZLT. Okay? So, by replacing Zn by this term and taking Zn minus Z naught over Zn over Z naught plus Z naught, and taking the real part together and the imaginary part together, we can represent the reflection coefficient in this case as the real part would be Z1 multiplied by ZL minus Z0. And if we are going to multiply by the denominator of Zn, it would be Z0 multiplied by Z1. So in this case, the real part would be Z1 multiplied by Z load minus Z0. Right? The imaginary part here, Z1 multiplied by Z1T. So we have Z1 squared multiplied by T. Minus Z0, when it would be multiplied by the denominator of Zn, would have plus JZLT multiplied by Z0. So we have imaginary part minus Z0 ZLT. So the imaginary part is JT multiplied by Z1 squared minus Z0 multiplied by Zn. In a similar way, we can obtain the denominator Zn minus Z0 as Z1 multiplied by ZL plus Z0 plus JT multiplied by Z1 squared plus Z0 Zn. Alright? This is the reflection coefficient as a function of t, which is actually function of beta, and beta is 2 pi over lambda, and lambda is c over frequency. So this is actually the reflection coefficient as a function of the frequency. This t includes the effect of the frequency. Alright? Okay. As we said, we have designed Z1 such that Z1 equals square root of Z0 Z load, or Z1 squared equals Z0 ZL. So Z1 squared minus Z0 ZL, this term would be 0. Alright? Now we have Z1 multiplied by Z load minus Z0 over Z1 multiplied by Z load plus Z0 plus GT Z1 squared, which can be replaced by Z0 ZL plus Z0 ZL. So this actually can be represented as 2 Z0 ZL. Right? And we can divide both the numerator and denominator by Z1. So this would be ZL minus Z0 over Z load plus Z0 plus JT multiplied by 2Z1 squared. 2Z1 squared over Z1, it would be 2Z1. Z1, it can be replaced by square root Z0 ZL. So this would be J2T square root Z0 ZL. Alright? This is the reflection coefficient as a function of t, where t is a function of beta and beta is a function of frequency. So this is a reflection coefficient as a function of the frequency. We are not interested in the reflection coefficient as a complex value. We are interested in the magnitude of the reflection coefficient. So the magnitude of the reflection coefficient is the magnitude of the numerator over the magnitude of the denominator. The denominator is composed of a real value plus imaginary value. So the magnitude of the denominator, it can be done as the square root of the real part squared plus the imaginary part squared. The real part squared is Z load plus Z naught squared. The imaginary part squared is 4t squared Z naught ZL. Alright? This is the magnitude of the reflection coefficient. Now, by dividing both the numerator and the denominator by the magnitude of z load minus z naught, and taking into consideration these brackets are to the power 1 over 2, so in this case, the magnitude of gamma, it can be represented as 1 over square root z load plus z naught squared over z load minus z naught squared plus 4t squared z naught z load over z load minus z naught squared. This squared because actually we have entered this value inside the square root. Okay? Alright. We can arrange z load plus z naught squared over z load minus z naught squared as z load minus z naught squared plus 4 z load z load. Okay? Z load minus z naught squared over z load minus z naught squared is 1. The remaining term is 4 z naught z load over z load minus z naught squared. Actually, this term is exactly this term except t squared. So we can take this as a common factor. It can be represented as 1 plus 4 z naught z load over z load minus z naught squared multiplied by 1 plus t squared. 1 plus t squared. Remember that t is tan beta L. So 1 plus tan squared theta is actually 1 over cosine squared theta or sec squared theta. So 1 plus t squared, it can be replaced by sec squared theta. This is the magnitude of the reflection coefficient. We can note that at theta equals pi over 2, the value of sec squared or 1 over cosine theta, it would be infinity because cosine pi over 2 is 0, 1 over 0 is infinity. So this would be infinity at theta equal pi over 2. It means that the reflection coefficient or the magnitude of the reflection coefficient when theta equal pi over 2, it would be 0. Now, if theta is not exactly pi over 2, we can calculate the reflection coefficient. Around pi over 2, the value of sec theta is still large value. So we can approximate 1 plus this large value as this large value only. So around theta equals pi over 2, we can approximate that the magnitude of the reflection coefficient, instead of 1 plus so and so, we are going to take this term only. 4 z naught z load over z load minus z naught squared sec squared c. But take into consideration this is to the power 1 over 2. So ignoring this one, this would be sec theta, and this would be z load minus z naught, and this would be 4 square root, 2 square root z naught z load, right? So around theta equals pi over 2, we can say the magnitude of the reflection coefficient nearly equals 2 square root z naught z load. Here, the denominator of the denominator, it would be the numerator, the magnitude of z load minus z naught without the square because we have square root. Here we have 1 over sec squared theta. 1 over sec is 1 over cosine theta. So 1 over cosine theta, we can say that is the magnitude of cosine theta. And because we are talking about the magnitude, all of these elements should be positive only, so we take the absolute value of this element. Okay, so the magnitude of gamma around theta equals pi over 2 equals z load minus z naught over 2 square root z naught z load multiplied by the magnitude of cosine theta, where theta is near pi over 2. By drawing this function, we can represent the reflection coefficient around angle theta equal pi over 2. At pi over 2 exactly, the reflection coefficient is 0, but when we move in slightly positive or slightly negative around pi over 2, we have higher reflection coefficient. And as I mentioned, this angle theta is actually beta L, and beta is 2 pi over lambda. So effectively, uh, the change of theta corresponds to the change of frequency. Okay, so this is the can be translated as the operating bandwidth of the quarter wave transform. In the following video, we are going to study this curve in more detail. Okay, all right.